So, what we have seen in the last class is that how to treat unsteady flow behavior, and while treating unsteady flow behavior, we have also seen that for the very simple case of a plate suddenly set in motion in an infinite body of fluid, the penetration depth of the motion, penetration depth of the effect of the motion of the plate is something which can be expressed in terms of an error function, in terms of a mathematical function also known as error function. Beyond that point, the effect of the motion of the plate is simply non-existent. So, any velocity gradient that you would expect is only going to be between the point and the penetration distance, because in this layer of the fluid, the velocity varies from that of the solid plate to 0, because the fluid here is stagnant. So, any velocity gradient that would exist in this distance only, and beyond that distance the gradient is essentially 0. Now, that is interesting, because unless and until you have a velocity gradient, you would not have transport of momentum, because the viscous transport of momentum, which is only present in laminar, which is the only mode by which momentum gets transported in laminar flow, it can work only when there is a velocity gradient. If there is no velocity gradient, there is no transport of momentum. So, all the transport phenomena that you can think of in terms of momentum transfer is limited in a layer close to the plate, and nothing happens beyond that point. So, with that knowledge, with that understanding from our previous problem, we now embark on a journey to understand what happens near a solid liquid solid fluid interface. This is extremely important, which with applications in a multitude of problems that we encounter every day, in the design of a fast moving vehicle, to the design of a rocket, to sports. Everywhere you would see what we are going to learn, what we are going to discuss in the 4 or 5 classes from now on, and I will give you examples of that. But it's time for a brief lesson in history. This theoretical hydrodynamics, it existed for a long time. The concept of viscosity and Navier-Stokes equation came a bit late. So, in the early 1800, the major industry at that point, the cutting edge technology, was to design ships. How good the design of your ship is, how effortlessly you can move that ship at a high velocity in water. That was the big thing at that point, at that instant of time. So, the Euler's equation was available at that time. Now, the problem that the designers of ships at that time, what they found is that the existing equations do not tell you much about the force which is needed to move the ship in seawater, for example. So, the reason that is it's the effect of the viscosity, so to say the effect of drag, was not incorporated into their calculations. And then came the equations, the Navier-Stokes equation and all, which took into account the viscosity and therefore the drag of the fluid on the surrounding fluid on the moving ship. But the problem is not solved as it is. There is, first of all, there is a huge departure between the theoretical results predicted from Euler's equation and the practical drag that is experienced by the moving ship. Even when the concept of Navier-Stokes equation came, it was almost impossible to solve. It's a very complicated equation. and if it's a two-dimensional flow case, then a solution of that Navier-Stokes equation in the entire flow domain surrounding the moving ship was impossible at that time. So then came someone with a bright idea, as always does. His name was Prandtl. What he demonstrated, what he conceptualized and demonstrated, that all these viscous transport of momentum is taking place in a layer very close to the surface of the ship. So if a ship moves in water only in a layer very close to that of the ship, the effect of viscous transport of momentum is important, or in other words, the Navier-Stokes equation is applicable. Viscosity is important. The velocity varies from that of the ship to the surrounding fluid, let's say the seawater, whose velocity, let's say it's 0. So the velocity varies from that of the ship to that of the sea in a region very close to the surface of the ship. So all the velocity gradients that you can think of is confined to a region, very narrow region close to the ship. You need to solve the Navier-Stokes equation, the complete Navier-Stokes equation of motion in that thin region. And once that you understand and you define the region to be very thin, where viscous forces are important, there would be some other approximations which can then be introduced to make our life simpler. Any point beyond that region, the fluid can be treated as inviscid, and therefore Euler's equation, Bernoulli's equation, Euler's equation, which is the starting point for Bernoulli's equation, which is Euler's equation is for inviscid flow. For fluids with zero viscosity, Euler's equation can safely be used for that region. So the entire flow domain around a ship can now be defined as consisting of a very thin region and any region beyond that viscous flow, inviscid flow. So this was the missing link between theory and experiment, which Prandtl provided with the concept which he calls as boundary layers. So boundary layer is that thickness of the fluid in which there is a gradient in velocity, and when we talk about the thermal boundary layer, where there's going to be a gradient in temperature, and if we talk about the mass transfer boundary layer, we will talk about the concentration boundary layer in which there is a concentration gradient. So velocity gradient for hydrodynamic boundary layer, thermal gradient for temperature temperature gradient for thermal boundary layer, and concentration gradient for the concentration or mass transfer boundary layer. These three boundary layers are different. So this is something, a concept which is extremely important, which gave rise to the ideas of a hydrodynamic boundary layer in which momentum transport takes place, a thermal boundary layer in which the transport of heat is taking place, and a concentration boundary layer in which the transport of a species is taking place. In essence, these boundary layers combine the collective heat, mass and momentum transport process which are taking place near a solid liquid interface, and which is physically the most important region that one should analyze, one should examine to decide or to predict what would be the total transport of heat, mass and momentum, or what can be done as an engineer to ensure that you have higher heat transport, mass transport or momentum transport from that point. And where it is going to be used? You have seen, all of you have probably seen the racing cars. The racing cars, when they are all aligned, okay, and they start to move, you would see that they all follow a pattern. There would be one car in the front, there would be another car very close to the front car, very close to the rear end of the front car, and it's going to stay as long as possible in this location, that is very close to the front car, right over here. And there would be a third car which is going to follow the second car, and it's going to be close to the end of the second car. So it's going to there would be a formation like this. Each car would like to have its nose at the end of the car just in front of it. Now, why does that happen? Whenever a car moves in at a high speed, a boundary layer is formed on the car. Now, whenever this boundary layer is formed, it's going to start. So let's say this is your car, and you see what's the design of a car. Each car is streamlined, so to say, so as to reduce the drag as much as possible. So it's moving at a very fast speed, and it's going to encounter the air over it. So the air comes in, air flows, forms a boundary layer, comes to this point, and then it goes away. Now, the air molecules which are over here, they have a certain momentum associated with it, but at some point it's something going to happen which is called the boundary layer detachment. The boundary layer which was attached to the surface, it's going to detach itself from this point and will form a wake. All of us know what wakes are. So when anything moves at a very fast velocity, there would be a region at the back end of it which is a wake, and which is essentially a low pressure region. So in racing cars, you would see something which is called a spoiler. So you have a spoiler which is something like this, a projected part near the end. The only purpose of that is to break the wakes which are formed on such surface, because if this is the low pressure side and this is the high pressure side, due to the stagnation pressure, since the air is going to come, hit it, and will probably at some point it will come to a zero velocity. So you have a high pressure at the front end and a low pressure at the back end due to the formation of the wakes. Then your drag, the pressure drag, is going to slow this car down. So pressure drag and friction drag, these are the two major drags, but the pressure drag is going to create a low pressure region in it. So if I am the second car, and if I have studied my transport phenomena, and I'm doing it intelligently, I would always like to keep the front end of my car in the wake which is formed by the first car. So the wake region over here is low pressure. So my front end does not experience a high pressure. It would experience an artificially low pressure created by the wakes formed by the first car. So the second car would always follow the first car, keeping its nose in the wake of the first car, and the third car, fourth car, and so on. So if you do it this way, then the wear and tear on your tires, on your engine, your fuel consumption, everything would be less, and you try to overtake and take the lead position only during the last lap, where you would like to come to the front. So by that time, the front car, it has endured enough of high pressure which will slow it down in the final lap. So you try to overtake it towards as late as possible and take the lead position, and you are fresh because your front end all this time has been exposed to a low pressure. So that's an example from the design of cars, streamlining of cars, the shapes that you see in modern cars, in buses, in trains, in planes, in space shuttle. All of them, the outer surface is designed in such a way to reduce drag, to improve fuel efficiency, and so on. In fact, the re-entry of rockets back into the Earth's atmosphere, is the velocity gradient is so large near the surface that it will create such a huge friction that it starts to glow, which we have seen, the pictures of which we have seen. And in the field of sports, the use of boundary layers is extremely interesting. Towards the end of this part of the course, I'll tell you that you all know, many of you are probably interested in cricket, and you know that when a fast bowler bowls at you, it may start to swing. What exactly is swing? That is, the ball is coming straight towards you. So you have taken a stance to go into the line of the ball and to play, but suddenly in mid-air the ball changes its direction and either move away from you, which is outswing, or come towards you, which is in swing. So, but at that point of time, you are already committed to play it in a certain way. You have already picked the line of the ball. Now, if the last moment the ball starts to deviate from its line, then you are bound to make a mistake. So, the seam bowlers always do this, and as their name suggests, the seam, they use the seam of the cricket ball to move the ball in air, either outswing or in swing. They are essentially trying to control the boundary layers on both sides of the ball. So, they would purposefully try to keep one side of the ball under laminar flow conditions, the other side of the ball in turbulent flow conditions. If you have two sides of the ball having two different roughnesses and you are using the seam to disturb the flow, then something interesting happens. So, we will see mathematically what it is later on, but always remember, when you watch a cricket game, if you see the ball moving in air, you know that it is due to the formation of boundary layer, different types of boundary layers on two different surfaces. It is also the reason that you would see the fielders and the bowler always trying to keep one side of the ball shining. They will never do the same thing on the other side. So, purposefully they would like to have one surface roughened and other surface smooth. If a surface is smooth, it is more likely that the laminar condition will prevail, and obviously a rough surface will initiate turbulent flow. So, the fielders, the bowler always try to rub the ball, keep the shine of the ball on one side and use it, let the other side gets rough. So, from automobiles to aeroplanes to cricket ball to basketball to golf, even to golf, you would see applications of boundary layers. You have seen the shape of the golf balls. The golf balls are never smooth; they have dimples on it. Okay, if you take a golf ball in your hand, you would see that they have dimples in it. So, these dimples on the golf ball, when you hit it at a very high with a very high velocity, what is going to happen is that it's going to disturb the boundary layers on it, and it would reduce the drag, and it would reduce the formation of the wake and therefore reduce the drag. So, if you keep two balls identical in size, shape and weight, only one is a golf ball, the other is a ball whose surface is very smooth, and hit it with equal force, with the equal in the same direction, our normal understanding would be that the golf ball with dimples on it will not go further and the smooth ball will go further. But it's just the reverse. The golf ball with dimples on it will cover a larger distance as compared to the very smooth ball, which is due to the presence of the dimples, how they affect the growth of the boundary layer and the formation of the wake. So, the applications and the possibilities are endless. I have just I spoke about the hydrodynamic part of the boundary layer. So, there exists a thermal boundary layer, a concentration boundary layer, and situations in which all these three boundary layers are present. So, think of a hot object which is moving in air. A hot object which is moving in air is going to have a thin layer, hydrodynamic boundary layer, in which the velocity of the air varies from that of the bullet to the velocity of the air well above it. So, if it is moving in still air, the velocity is 0 here, but the velocity varies from that of the bullet to that of the air far from it. But when I say far from it, it is essentially a very thin region, because all boundary layers are very, very thin. Okay? All your transport phenomena are taking place in a thin layer. Now, the bullet is, let us say, it is hot. So, the air is cool. So, the temperature of the air close to the bullet will vary from that of the bullet, since the temperature has to be equal at the solid liquid interface, to that of the fluid. Okay. Now, think, so that is what is called the extent to which the effect of temperature has penetrated is called the thermal boundary layer. Now, think that bullet is made of naphthalene right now. So, if a naphthalene bullet travels through air, the naphthalene is going to go through the sublimation process, and the concentration of naphthalene very close to the bullet is going to be maximum, and as you move away, the concentration of naphthalene is going to fall to a value equal to 0, because the air does not contain any naphthalene. As a result of which, a mass transfer boundary layer will form around the moving naphthalene bullet. So, you can see that 3 different types of boundary layers are possible. One, which is the hydrodynamic boundary layer, where we deal with velocity. The second is the thermal boundary layer, where we deal with the temperature, and the third is the concentration boundary layer, where we speak about the species concentration as a function of its distance from the moving object. The thicknesses of all these 3 layers can be, and in most cases will be, different. So, we will have the governing equations will also be different. The approximations which are used to reduce, to simplify those equations are similar, fundamentally similar in nature. So, the combined application of thermal, hydrodynamic and concentration boundary layer, the field is enormous. It is a well researched field, but still we do not have all the answers. And if you think of let us say we are restricting ourselves so far to laminar flow, but the boundary layer is never going to be laminar. Beyond certain distance, the disturbance of the moving object would be such that the flow inside the boundary layer will change itself from laminar to turbulent layer. The moment it becomes turbulent, the amount of momentum transfer, heat transfer or mass transfer will increase significantly. The thickness of the boundary layer, the layer close to the surface of the solid, which is called the boundary layer, when the thickness of the boundary layer in a laminar flow grows rather slowly, but the moment it becomes turbulent, it starts to grow rapidly. So, the behavior of the transport, the thickness of the boundary layers, all are going to be different when there is a transition from laminar to turbulent flow. So, that is something which we have to keep in mind. And we would see that it is not possible always to get an analytic solution. We will have to resort to numerical techniques, and especially in the case of turbulent flow, we will have to use some approximations. Instead of the differential analysis of motion, which would give you the velocity at every point in the flow field, at certain point we would have to resort to other techniques which are known as integral techniques, the integral methods to deal with flow, where you are more interested in finding out the averages, not the values at every point. So, all those will come into our discussion of boundary layers. But let us look at this figure first. What I have drawn here is, this is an airfoil, okay, which is moving in air, and you have the air, this is moving. So you have the upstream velocity. You can think of this as the relative velocity u infinity with which the air approaches the airfoil. At this point is the stagnation point. So these are streamlines of the liquid which form along the airfoil, and the point where it hits the airfoil is called the stagnation point, and the stagnation point would give you the highest pressure. And at this point the boundary layer starts to form. It's first going to form the red dotted line what we have over here. Initially it will remain laminar, so it's laminar boundary layer, and at some point it will become turbulent, and it will form, the thickness will rise rapidly, and it may even detach itself from the surface of the airfoil, and which is going to give rise to viscous wakes that we talked about. So as a result of this, as a result of the formation of layers and all, the airfoil experiences a net force as a result of shear and pressure forces acting on its surfaces. So we all know how the aeroplane lifts off from the ground, and the forces which are experienced by the airfoil because of its shape, there is going to be a component parallel to the flow of air, which is called the drag force, the component of force which is called the drag force, and there would be a component perpendicular to u infinity which is known as the lift. So the drag force also have two components, one which is called the pressure drag, and the second which is called the viscous drag or the shear drag. Okay. So these are something which we are going to discuss in over here. Now the situation here is extremely complicated, as you can see that there are so many things we have to keep in mind. The problem that we have in here is, let's say the simplest possible case, I have a solid plate over which some fluid is approaching this. This is my y direction and this is the x direction. So at this point and on the solid plate, the velocity is going to be 0. But if I move slightly up, there is going to be a velocity in here which is not going to be equal to the velocity of the approach velocity. This is called the approach velocity of the stream. It is going to be slightly lesser than that. So if I draw the contour of the point at which I can sense the velocity, then this is known as the boundary layer thickness. So the velocity is going to be 0 here, and the velocity is going to be equal to the approach velocity in this case. So the imaginary layer is known as the boundary layer. So if I draw it if I simply magnify this region, and the velocity here is going to be 0, the velocity is going to be slightly more, even more, and at this point over here it's more or less going to, if this is v, approach velocity v, the velocity is going to be equal to v. So the profile looks something like this. So the velocity changes from a value equal to 0 to that of the approach velocity for flow over a flat plate over certain distance, and this distance over which the velocity changes from 0 to v is called the boundary layer thickness or the disturbance thickness. This boundary layer thickness is once again I would say that to repeat that the velocity changes from 0 to that of the velocity above it over a certain distance, and beyond this point the velocity does not vary at all. So, from here to here the velocity varies from 0 to v, but once it reaches v at this point, from this point onwards the velocity does not vary. So, the location at which the velocity reaches the free stream velocity is called the boundary layer thickness. The point beyond that there is no change in velocity and the flow here is inviscid. That is, there is no viscosity. In here the flow is viscous. But generally it is not the attainment of the velocity equal to the approach velocity which is used to demarcate the boundary layer. It is when we say that Vx is about 99% of V, 99% of the approach velocity for a flat plate. This location, the y location where Vx is equal to 0.99 V is called the boundary layer thickness delta. So, once again the boundary layer thickness delta is defined as the y location where the velocity reaches 99% of the free stream velocity. This velocity is called the free stream velocity. Why it is called free stream velocity? Because it is free from the effect of viscosity, and for the case of a flat plate this approach velocity and free stream velocities are equal. In general, free stream velocity is defined as u infinity. For a flat plate the approach and the free stream velocities are equal. So, whether you write 0.99 V or 0.99 u infinity, it really does not matter for flat plate because V and u infinity are same. But on a curved surface u infinity can be different from V. So, I think the correct definition would be 0.99 u infinity. For a special case u infinity is equal to V for flow over a flat plate, but the definition of boundary layer should be the value of y at which Vx is 0.99 of u infinity. We will discuss it once again in the next class, but what I have done here is introduce the concept of boundary layers from a historical perspective, discussed some of the interesting applications of it, and started to give you the definition of what is the boundary layer thickness. There are so many things to cover in this part. So, we will start with the thickness of the boundary layer, whether it is approach velocity, free stream velocity, and we would see that it is very difficult to experimentally measure what is the boundary layer thickness, because it varies slowly and merges asymptotically with the free stream. So, if it is varying slowly and merging asymptotically with the free stream, it is difficult to pinpoint the exact location where the velocity inside the boundary layer becomes equal to 99% of the free stream velocity. So, there are ways, different methods have been suggested to alleviate this problem, to address this problem, where we can say with some confidence that whatever we call as the thickness of the boundary layer is correct. Okay. Because the experiment, there could be large experimental errors to decide the location where V is equal to V, the velocity inside the boundary layer is 99% of the free stream velocity. So, those things we are going to, those more detailed description of boundary layer, both descriptive as well as mathematical one, we will take up in the next class.